Hey everyone, back with another video lesson for the Calculus and Vectors course. Today we're going to make some connections with exponential functions. So basically do two applications together and maybe tie in some trig functions as well. So I should go pretty quick. Yeah, just two big applications. Why don't we get started? The first application will be on about medical treatments. One application of exponential decay is you can use it to model the amount of a drug or a treatment in your system. So here we're using an isotope of gold treating liver disease. So we start off with a initial value, a 6 milligram sample is injected into the liver. And then this, after 1 day, this decays to 4.6 milligrams after 1 day. And we're going to assume that the amount left in this system is modeled by an exponential function, a decreasing exponential function with a base of e. And n naught, or n sub 0 there, is our initial value 6. And just want to note, this is actually a typo. That should be days. I mean, you could do minutes, but it's much easier to do days. So we're going to work with days here. So we're going to play around with this a little bit. We're going to, so traditionally, like you guys might have been able to model something like this after your grade 11 course, but you haven't exactly modeled it with the Euler's number e as the base. Notice it's e to the power of negative lambda times t. So we know that e to the power of x, I better switch to something lighter now. The function e to the power of x, e is just a number, about 2.7-ish. It's an increasing exponential function. Remember, so if you have like a positive base, or not positive, bigger than 1, and then with a negative on the variable, so thinking back to grade 11, that means a reflection in the y-axis. And so e to the power of negative x actually is just one way of modeling a decreasing exponential. So let's get started. So this, we've talked about what things in this equation mean. N naught is the initial value 6. E is our base. We know that number. And the only thing we don't know is lambda, this constant, this disintegration constant we're going to use here. Lambda is used a lot in physics. Usually, those of you guys who took grade 11, remember that you use it for wavelength. Here we're using it to kind of tell us how fast our substance is decaying. All right, so let's get started for the disintegration constant. So taking our equation here, we know that after 1 day, there's 4.6 milligrams left. So when t equals 1, we're left with 4.6. And naught, the original, is 0. Base of e, we don't know what lambda is, but we know that when we plug t equals 1 in, we get 4.6. We can solve this equation for lambda. 4.6 equals 6 times e to the negative lambda. We've talked about the tools to do this, so let's just grind it out together. I'm going to do it with you guys. I'm going to just do it one step at a time, maybe keep a bit of accuracy along the way. So when I divide it by 6, I got about 0.7667 equals e to the negative x. I'm going to take the ln of each side. And if you can do this in less steps, then that's great, if you're comfortable doing that. And we can bring down the negative x. And we know that the ln of e is 1. And so we get ln of 0.7667 equals negative x. I'll even write this out, times the ln of e. But hopefully many of you guys are just at the point where you don't have to do that, because you know that the ln of e is 1. And that ln e of anything is just that argument. So here, negative x. That's equal to 1. And so x is equal to the negative of ln of about 0.7667, whatever that is. Oh, I changed lambda to x along the way. That's okay. This is just what happens when you shoot things on the fly. So we'll just, it's lambda. Yeah, it's because my lambda looked like an X there. Lambda, lambda, lambda. Usually at this point of the course, we can I usually make some Half-Life 3 jokes, but there kind of is a Half-Life 3 now. All right, so lambda, negative ln of 0.767. Let's get that done. All right, so about, I'm going to go to 3 decimal places here, about 266. All right, so another way, so we can write out our equation then in full to model the amount of gold 198 left after a certain amount of days, initial value of 6, a base of E, and our disintegration constant 0.266. All right, so this is one way to model this equation. Let's move forward. Next, we're going to determine the half-life of gold 198. So we want to determine how long it takes for the substance to disintegrate to or decay to half its value. So we're going to use our new equation we made up. And we're concerned about when, so just to flip back, we have our equation. Now we want to know, when is n of t going to be 3? When will we have, what value of t gives us 3, half the amount? So we're going to plug in 3 to our equation. Equals 6 e to the negative, I think it's negative 0.266 times t. And we're going to solve this equation for t. So we're just solving another exponential equation. We just did one together. We'll do another one. So we got 0.5. This time we're solving for t instead of lambda. In the first one, we knew t, we're finding lambda. This time we know lambda, we're finding a t. So I divided both sides by 6, exactly 0.5. 266t. So at this point, maybe you're comfortable enough to know if you just rewrite that as a logarithm or take the ln of each side, you're going to get the ln of 0.5 equals negative 0.266t. This is just doing what we did in the last question exactly, just shaving off some steps. And so t is whatever the ln of a half or 0.5 is, divided by approximately negative 0.266. So the ln of 0.5, because 0.5 is below e, that'll be a negative. And when we divide by a negative, this will give us a positive value. So we don't need to worry about all those negatives floating around. We are going to get a positive time. Okay, so very close to 2.6. Let's say 2.61. So what this is saying is every 2.61 days, the amount of this isotope of gold treating the liver, half of it is left. So after initially there was 6, in 2.61 days, there'll be 3 milligrams left. In another 2.61 days, there'll be 1.5, et cetera, et cetera. So we've got the half-life. Now, what we can do with that is we can write the equation in a new way that tells us instead of this disintegration constant we found, we can write the equation in a way that uses the half-life. You might be familiar with this method from your grade 11 course. So the initial value is still the initial value, 6. But if you want to write something in terms of its half-life, we're going to use a base of 0.5 or half. And the way to implement the half-life is to put it in the denominator of a rational expression in the exponent, t over the half-life, which we found was 2.61. This is just another way to express it. And you can just kind of verify this works. Like imagine if we plugged in t equals 2.61, well, then that exponent would be 1, and you'd have 6 times 0.5, you'd have 3. You get half of what you had. So it makes sense that this function works. So this is a separate way to write this function out. Before we actually do some derivatives, I actually want to compare two things. So we now have two I'm just going to write this. You probably have this in front of you. I'm just going to write it down for myself. We have two ways of writing this out, this function. We have what we just did with the half-life, and we had our earlier function. I just flip back for the disintegration constant. It was negative 0.266. Two different ways to represent the same function. Those are the same function. If we ignored all the rounding, like they're the exact same function. And just to show, you can do this little calculation yourself. Try doing 0.5 to the power of 1 over 2.61 and see what you get. And then try doing e to the negative 0.266, because those are the places where these functions differ. They each have a 6 in front. They each have a t in their exponent. This is the stuff that differs. And hopefully what you see is that these are, for the most part, equivalent. 0.5 to the power of 1 divided by 2.61. I got about 0.7, I'll just put 0.77-ish. And I'm expecting it to get the same thing when I do e to the power of negative 0.266. And I do, they're pretty close actually. So just wanted to compare that with you guys. Let's use one of our equations to look at how fast the sample is decaying after 3 days. How fast is the drug leaving the liver at that point? So how fast is it decaying? So we're looking for a rate of change derivative. So we've got to decide which of these we want to work with. Now, the nice thing about the Euler's number is that we've been seeing the derivative is really easy. That's why a lot of times these exponential functions will be written in terms of Euler's number. And when you take some physics courses, biology, chemistry, etc., moving forward, you're going to be using Euler's number a lot. It's just very convenient for the math. So let's use that one for our work here. So just going to one more time rewrite my function. Again, I think you guys have this several times on your page, but I don't have it on my slide here. Negative 0.266 t. Let's find the derivative. N prime at t. The 6 does not affect the derivative. The derivative of an exponential with a base of e is itself, which is why it's nice to use. Except we have a function in the exponent. We have to multiply by the derivative of that function, which is just negative 0.266. So nice and easy. I don't think we really need to simplify because we're concerned with what the rate of change is after 3 days. So we'll sub in 3, and you guys can do this calculation at home. I will do it right now as well. Notice we are going to get a negative number because exponentials are always positive. So let's do this. E to the power of negative 0.266 times 3 times 6 times 0.266 negative. So I got about negative 0.72. And this is, remember, N of t is in milligrams, and t was days. So this is milligrams per day at this point. So whatever amount of drug we had in the liver after day 3, in one more day, approximately 0.72 milligrams less than that is what we can expect. And that's just an exponential function application, something you guys did in your grade 11 course, but now just talking about it in terms of Euler's number and trying to make some connections there. Let's look at another example. This one ties in. This one's really interesting because it ties in exponential functions and trig functions. Because most of you guys have taken physics and have learned about either Hooke's law, learned about pendulums, and used waves to model that. It's periodic motion. But intuitively, most of us know that when you swing a pendulum, when you bring it back and let it swing back and forth, it's not going to swing forever because you've got friction in the string or what have you. You've got air resistance in terms of a spring bouncing up and down. You've got friction in the spring, and eventually it settles and it's going to stop, right? So instead of a periodic function, what we're going to have is something where the amplitudes of those get less and less and less, right? And so we've got periodic nature there, but we also have those maximums and minimums decreasing over time. And so damped oscillation, so things like shock absorbers in your car or on a mountain bike, tons of applications. A pendulum losing energy over time. They're all damped oscillators, and they can be modeled by a combination of exponential functions and periodic functions. So you can see our function here. So we have a, in this case, like the shocks on a vehicle's body going over a bump. So we've got sine t, which is kind of gives you the periodic nature. The springs, we've all been in a car going up and down and see the shocks. It just takes a little while to settle. So we've got that periodic nature. And then we have this decreasing exponential to take care of the fact that those oscillations are just decreasing over time. What we're going to do here is we're actually going to show how to sketch a function like this. I've given you an idea of basically what it looks like, but we're going to kind of go through the math a little bit. So yeah, let's do that. I'm going to just rewrite. Well, first I'm going to move my handsome face up there. I'm going to rewrite my equation on here as well, so I don't have to keep flipping back and forth. H of t was, just want to be careful, e to the minus 0.5 t. Right. So an easy point to find is to plot the y-intercept. So I'm going to squeeze a in here. I might do a and b, maybe c, and then just erase this, and I'll work on the same slide here, and you'll have all this work on your paper. Plot the h-intercept. So we're finding what is h when we plug in 0. I mean, you can probably see right away we're going to get 1 from the exponential, e to the power of 0, and we're going to get 0 from sine of 0 is 0. And so h of 0 is 0. And so this might be annoying switching colors back and forth, but whatever. It is what it is. I'll use green for plotting some points. Okay. Actually, green might show up okay in this background too. Yeah, it shows up okay. So let's do part B. When will this function have a value of 0? So now we're asking, when are the t-intercepts? So if this oscillator is going up and down, when are we coming back to like equilibrium? And there's going to be many solutions, right? So let's see what the math looks like. So we're asking, when is h equal to 0? And we've been having discussions about solving equations with exponentials and trig expressions in them as well. We think about what makes this equation equal to 0. Well, e to anything can never be 0. So we almost don't care about it. Like this, if we're asking when does this equation equals to 0, this equation equals 0 whenever sine of t equals to 0. And we know that from earlier courses. And we should be, I should make a point too. In this question, because we have trig stuff and exponential stuff, that means we must be work in radians, a dimensionless variable. So make sure your calculator is in rad mode. But in terms of when is sine t equal to 0, it's at 0 and then any multiple of pi, right? Pi, 2 pi, et cetera, on our graph. So pi is about 3.14, 2 pi about 6.28, and then 9.42. So on our graph, our spring will come back to equilibrium at those 3 times, but it's going to keep bouncing back and forth mathematically forever, but eventually it's just going to be so tiny we won't even notice it. So for our graph, that'll look fine. All right, so let's do part C. So I'm going to erase my work here, I think, and just work in this space again. So we're going to find the derivative, find the first 3 critical points. So what this will correspond to is our first 3 points where the spring either goes, the highest it goes, or the lowest it goes, and then the highest. So kind of those big extremes, we're going to find those first three, add them to our graph. You might expect one of them to be between 0 and pi. We're going to be going up. We're going to come back down, go back up. We're just going to see where those values are to give some shape to our graph. So let's keep moving forward. I don't want to write with my eraser. I'm posting these to YouTube, but it's definitely not polished YouTube content for sure. Just like me doing a lesson like it would be with you guys in front of a class. So, all right, let's find the derivative. Okay, so our function is a product of two functions. So we have to use the product rule. So h prime of t, we differentiate the first guy, which is just e to the negative 0.5t times negative 0.5. Leave the second function alone, sine t, plus we leave the first guy, e to the negative 0.5t, and differentiate the second, cosine t. When we factor out the exponential, we're left with, I'm actually going to write we're left with from the second guy, just cosine t, and from the first guy, negative 0.5 times sine t. And we're going to be setting this equal to 0, right? Because we're looking for critical points when the tangent line's horizontal, our local max and mins. And so you can see, just like with part B, we're going to have an exponential part that we don't care about. What we do care about is what makes the trig stuff equal to 0. So I'm going to squeeze a bit of work in here and then maybe go up to the top right and erase that stuff. You can organize your work however you'd like on in your notes at home. So we're looking for, when does cosine t minus 0.5 sine t equal to 0? So we have cos t and sine t. If you recall, a strategy I share with you guys is we want to write this in terms of one trig ratio. And we can do that if we divide everything by cosine. So let me show you what I mean by that. So I'm going to get sine t by itself. Actually, I might just, let's sine t, let's do that. Move it to the right, it would be positive, and then we'd have cos t on the left. Maybe I should have switched those over. It's not a big deal though. But we're going to divide both sides by cosine. And recall that sine of an angle divided by cosine of the angle, that's equivalent to the tan of that angle. That's called the quotient identity. So I divided both sides by cosine t, right? And so I'm left with that. And if you solve for tan t, we get 2. So we're looking for values of t that give a tan of 2. And so we're going to have to resort to our calculator and the cast rule. So if you guys want to make sure you're in radians mode and find what your calculator gives you when you do tan inverse of 2, I'll do the same thing. Got to make sure I'm in rad mode too. I am not, so I'm going to fix that up for sure. All right, so I'm in rad mode. So tan inverse of 2, I got about 1.1. Switch back to green here. So tan inverse of 2 is about 1.1. So that's our first value for t. We'll calculate the y value in a second, but our first maximum will be around 1 times 1.1, and we'll calculate what that is in a second. We're going to get 3 more values. It's going to go up, kind of come down between pi and 2 pi, and then back up again. So let's find 3 more values. But how do we do that? So we're going to use the cast rule. We just got 1.1. So thinking about the Cartesian plane and how we talk about angles. So 90 degrees, 0 is positive x-axis, positive y-axis is 90 degrees, or pi over 2 radians. Pi divided by 2 is 1.57. So 1.1 radians is somewhere in here. This isn't a perfect diagram. It's somewhere in there, right? And we know from the cast rule that other angles where we're going to get, and this is 1.1 radians, other angles where tan will be positive is down in the bottom left. And so another solution will be whatever is 1.1 radians past pi radians. So I'll call that T1. T2 is equal to whatever pi is, 3.14 plus 1.1. Let's just go to one decimal place. So around T2, around 4.2 seconds, we're going to have another, in this case, it'll be a minimum. And then a third time will be, all the way back around 2 pi plus 1.1. So 2 pi is 6.28 plus another 1.1, 7.38. Or 7.4, I guess, if I'm going to one decimal place. So somewhere right about there. So let's quickly figure out what those y values are, plug those into our original function. So if you want to do this, like pause the video and like fast forward it, it's probably not too fun watching me type in calculations. So you know what? Actually, I'm just gonna let you guys do the calculations here, and just put a rough value on the graph. So you guys are gonna find a y value somewhere up here for 1.1, somewhere a bit less than that for 4.2, and something a bit less than that for 7.4, something like so. I don't know if that's exactly what the y values are, but it'll look something like that. And so you get this cool graph that mixes both exponential and periodic. So these max and mins are just going down. And the next one would have an even lower max, and then it just almost becomes like kind of flatlined. So that was part D. Basically, you guys are plugging y values in and finding that max, that min, that max. And you can see the max displacement here. It's going to be whatever you get when you plug in t equals 1.1. Yeah, I just thought that's not going to be fun for you guys to watch. One other thing I add to this graph here is if you plotted all the max and mins, what you get is you actually get that this periodic wavy function, not quite periodic because the amplitude's changing, is actually bound between two functions. It's bound between the function y equals e to the negative 0.5t and y equals negative e to the negative 0.5t. Because if you think about it, if I go back to the original slide there, sine t is always, like whatever t is, it's never going to be below -1 or above 1, right? And so as those values of sine t go between their max, go between 1 and -1, you hit the function above the x-axis, e to the negative 0.5t, and below its vertical reflection, negative e to negative 0.5t. So you get this wavy semi-periodic function with the amplitudes decreasing and bound by these exponential functions. So pretty cool. Those of you guys who move forward with the sciences will see a lot of damped oscillators. So I hope you enjoyed those connections there. Next steps, I've got some practice questions you can try from the McGraw-Hill-Ryerson text. Today is Friday shooting this lesson, so I'll probably get some review put together over the weekend. And Monday I'll have some review available, have kind of like a Unit 3 assessment available next week as well. And by the end of next week, I will be starting to shoot some lessons on the vectors portion of the course. So that's it for today. Hope you guys have a good day, and we'll see you soon.